The next topic we study is going to be random walks on networks. In order to study that, we are going to need to work with matrices related to graphs. And so I want to begin with a quick review of some ideas from linear algebra that we will need for this. So let me start by sharing my screen. Okay, so we are going to quickly review some ideas from linear algebra, and we begin with the spectral theorem for Hermitian matrices. So first I should tell you what symmetric and Hermitian matrices are. So the notation we will use, we'll denote an n by m matrix over the real number consisting of real or complex entries by putting the size of the matrix in this superscript here. So an n by n matrix with real entries m is called symmetric if the matrix is the same as its transpose, meaning that for every I and j, the ijth entry is the same as the jith entry. If I take the transpose, these switch places, and so they should be the same. And very similarly, for complex matrices, n by n square matrices, we call a matrix Hermitian if it's the same as its Hermitian conjugate, m dagger, which is defined as follows. So this is the transpose with an complex conjugate. So M is Hermitian if the ijth entry is the same as the complex conjugate of the jith entry. So the star here denotes the complex conjugate. Okay, and a bit more terminology. We say that vector V is orthogonal to a vector W, which we write this way. We denote it by V per W if the inner product is 0, and the inner product is defined this way. Whenever we mention a vector, by default, it's a column vector, unless we say otherwise. So V and W are column vectors, and they are orthogonal if V dagger W is 0. So V dagger is the vector you get by taking the transpose of V and taking the complex conjugate of each element. Okay, so this is the conjugate transpose of V. And this reminder is how inner products are defined over complex vectors. Just a remark, we are going to be mainly interested in matrices with real entries, real valued matrices. But much of what we say carries over to complex matrices, and so I'll state the results for complex Hermitian matrices, though we'll mainly use them for real symmetric matrices. Okay, and the proofs also use complex numbers, so we do need them. Okay, so this is the main theorem. This is called the spectral theorem for Hermitian matrices. And it says that if M is a square n by n Hermitian matrix, then all of its eigenvalues are real. So it has n eigenvalues, and they are all real. If Vi and Vj are eigenvectors corresponding to distinct eigenvalues lambda I and lambda j, then these vectors are orthogonal to each other. And finally, M can be diagonalized. So it has an orthonormal basis of eigenvectors, and you can write M as the sum of these rank 1 matrices. So here Vi is a column vector, Vi dagger is its conjugate transpose, it's a row vector. So Vi times Vi dagger is from your perspective, a column vector times a row vector, which gives a matrix, an n by n matrix. And then we multiply that by the corresponding eigenvalue and add these up. Then the resulting matrix is M. This may not be the most familiar form in which you've seen the diagonalization, but what this is saying is that M is diagonalized by the matrix made up of these column eigenvectors. So if I call that matrix V, V is an orthogonal matrix, and Vm, V inverse is the same as V Hermitian conjugate. Vm, V dagger gives you the diagonal matrix of the lambda i's. This is another way of saying the same thing. Okay, provided the VI's are normalized to have unit length. Otherwise, you need the inverse rather than the Hermitian conjugate. Okay, take a moment to make sure you understand the statement of the theorem before we move on to the proof. It's important for us to understand the statement. Every Hermitian matrix has a complete basis of eigenvectors. The eigenvalues are real. The eigenvectors corresponding to distinct eigenvalues are orthogonal. These are the three statements that the theorem contains. Okay, so we'll prove most of this theorem, taking a little bit for granted. So first we'll show that the eigenvalues are real. Suppose lambda is an eigenvalue of the matrix M, and V is a corresponding eigenvector. By definition of eigenvectors, that says MV is lambda times V. So now let's multiply both sides of this equality by V dagger. So we get V dagger times MV is V dagger times lambda V. Lambda is a scalar, so it commutes with matrix multiplication. So this is just lambda times V dagger V. Okay. So next, let's evaluate the term on the left. So what's this row vector times matrix times column vector? Matrix multiplication is associative, so we can do this. We can first multiply V dagger and M, and then multiply the result by V. Now M is Hermitian by assumption in the theorem statement. So we can replace M by M dagger. Now, what is V dagger, M dagger? Maybe you're more familiar with the case of real vectors and matrices. What's V transpose, M transpose, or A transpose, B transpose for products of matrices? That's just BA whole thing transpose, right? So if you take the product of two matrices and transpose it, you get the product in reverse order of the transpose matrices. So V dagger, M dagger is the same as the Hermitian conjugate of MV. Okay, so we've replaced this by MV, but what's MV? That's the same as lambda V. So we have lambda V dagger V. Now the same way as before, lambda V dagger is V dagger lambda dagger. And what's the Hermitian conjugate of a scalar? So you have to transpose that and take the complex conjugate. The transpose of a scalar is just the same scalar. And so you have just the complex conjugation. So you get lambda star here. Okay, so it's lambda star V dagger V. Okay, so we've evaluated the same thing in two different ways. We've evaluated V dagger MV in two different ways, and so those two things should be the same. And so lambda times v dagger v is the same as lambda star times v dagger v. And so I want to claim from that that lambda equals lambda star. And to do that, I want to be able to cancel v dagger v. And I can do that if it's non-zero. It's a scalar, and I want it to be non-zero. And is it? Yes, it is, because v dagger v is the inner product of the vector v with itself, and that's the squared norm of v. And that's non-zero because v is a non-zero vector. By definition of eigenvectors, in the eigenvalue equation, there should be a non-zero solution. Zero is always a trivial solution for any lambda. So that doesn't count. The zero vector never counts as an eigenvector. Okay, so v is a non-zero vector, so its squared norm is non-zero, and so we can cancel that and conclude that lambda is the same as its complex conjugate, and the only numbers for which the only complex numbers for which that's true are real numbers. Okay, so we've shown that if lambda is an eigenvalue of m, then lambda must be real. Hence, all eigenvalues are real. So that's the first statement in the spectral theorem that we've proved. The next statement we want to prove is that eigenvectors corresponding to distinct eigenvalues are orthogonal. So let's move on to that. Say Vi and Vj are eigenvectors of the matrix M corresponding to distinct eigenvalues lambda I and lambda j. We are going to do the same sort of calculation. So we take the matrix product Vi dagger M Vj. So that's a row vector times a matrix times a column vector, which gives us a scalar. And we evaluate this in two ways. So first we multiply MVJ, that gives a column vector, multiply that by this row vector. Well, that gives us Vi dagger. MVJ is an eigenvector of M with eigenvalue lambda j, so MVJ is just lambda j Vj. And again, scalars commute with matrix multiplication, so this is lambda j times Vi dagger Vj. Okay, and then using associativity, this is the same as first doing the multiplication of Vi dagger with M and multiplying the result by Vj. Since M is Hermitian, we can replace that by Vi dagger M dagger, which becomes MVI whole thing, a Hermitian conjugate. But MVI is lambda I Vi. Taking the Hermitian conjugate of that gives us lambda I star Vi dagger. Okay, and since we've evaluated the same thing in two different ways, these two things should be the same. So lambda j Vi dagger Vj should be the same as lambda I star Vi dagger Vj. Okay, so if we subtract that, lambda j minus lambda I star times Vi dagger Vj should be 0. But lambda I is real. We've shown all the eigenvalues are real. So lambda I star is the same as lambda I. Okay. And this is real, and lambda I and lambda j are distinct. So this quantity here is non-zero. So a non-zero multiple of the vector Vi dagger Vj, of the scalar Vi dagger Vj should be 0. And that means Vi dagger Vj should be 0. And that's the definition of Vi being orthogonal to Vj, because this is the inner product of Vi and Vj. Okay, so we've shown the second statement in this in the spectral theorem, which is that eigenvectors corresponding to distinct eigenvalues are orthogonal. So what remains is to show that the matrix can be diagonalized, meaning that it can be expressed as the sum of these rank 1 matrices. Okay, and we are going to make one, so this is the one bit I'm not going to show, that there is a complete basis of eigenvectors. Let's take this for granted. This may not this doesn't happen for all matrices. You can have matrices for which there are repeated eigenvalues, but the geometric multiplicity of an eigenvalue is strictly smaller than its algebraic multiplicity. Meaning, for example, that an eigenvalue may be repeated 4 times, but it may only have 2 eigenvectors. That doesn't happen for Hermitian matrices. I'm not going to prove that, but I'm just going to assume it. So we have a complete basis of eigenvectors. If you take that for granted, then we've already shown that if these eigenvectors correspond to distinct eigenvalues, then they are orthogonal. What if an eigenvalue is repeated and you have, say, 3 times and you have 3 eigenvectors corresponding to it? Maybe they are not orthogonal to start with, but my claim is that they can be chosen to be orthogonal. So these 3 eigenvectors, okay, that's just Gram-Schmidt orthogonalization, which you've seen. So you have 3 eigenvectors. Start with the first one, take the second one. Maybe it's not orthogonal to it, but it has a projection onto it. So you can decompose the second eigenvector into something that's parallel to the first one and something that's perpendicular to it. So if you throw away the parallel bit and keep just the perpendicular bit, now that's also an eigenvector. That's just an easy calculation. And so you have now 2 orthogonal eigenvectors corresponding to the same eigenvalue. And then there's a third one, which is maybe not orthogonal to the span of these 2. But again, you can decompose it into something that lies in the span and something that's perpendicular to the span. And you can show the bit that's perpendicular to the span is an eigenvector with the same eigenvalue. And so by doing this, you can always get enough. You can get enough, or you started with 3 eigenvectors, you get back 3 orthogonal eigenvectors. Okay, so eigenvectors corresponding to the same eigenvalue can be made orthogonal, can be chosen to be orthogonal. Okay, and so we've now got a complete basis of orthogonal eigenvectors. So there are, we started with an n by n matrix, so there are n orthogonal eigenvectors, and then you can normalize them to have unit length, so we have an orthonormal basis of eigenvectors. Okay, and the claim is that if I write m as the, okay, and then the last bit I have to show that is that I can write m as the sum of lambda I, vi dagger. How do we show that? So so I want to show that m is the same as this matrix. And let's see how this matrix acts on the vector vj. So if I multiply the column vector vj by this matrix here, what do we get? We get the sum lambda I vi times vi dagger vj. But these are orthonormal vectors, so vi dagger vj is 0 if I is not equal to j, and it's 1 if I equals j. Right? That's what it means to be orthonormal. So all these terms are 0 except when I equals j, and then you get 1, so all we are left with is lambda j vj. But instead, if I use the matrix M and I calculated MVJ, Vj was an eigenvector of M with eigenvalue lambda j. So I just get the same thing, lambda j Vj. So I want to show that this matrix is the same as this matrix M, meaning that this matrix multiplying any vector x is the same as m multiplying any vector x. That's what it means for 2 matrices to be the same. So a matrix represents a linear map. So to show two matrices are the same, you have to show that the linear maps that they represent are the same, meaning that they map the same. So A and B are linear maps. They are the same if A maps X to the same point as B maps X for every possible X, right? So you want to show that this linear map acting on X is the same as M acting on X for every possible vector X. Have we done that? Well, we've done that for some vectors. We've done that for eigenvectors Vj for each possible j. So we've done it for every eigenvector of M. But why is that enough? The eigenvectors form a basis. So for a basis of the vector space, we've shown that these two matrices, these two linear maps are the same. Now, a linear map on a vector space is completely defined by what it does on a basis, right? Because every vector can be expressed as a linear combination of basis vectors. So if two linear maps agree on a basis, they agree on every linear combination of elements of that basis. And those linear combinations are all of the vector space. So these two matrices are exactly the same. Okay, so that completes the proof of the spectral theorem. Okay, so the second result I want to mention is another characterization of eigenvalues and eigenvectors of a Hermitian matrix. Now, eigenvalues are defined as numbers which solve this eigenvalue equation. So lambda is an eigenvalue of M if there's a non-zero vector V such that M times V is lambda times V. That's the definition of an eigenvalue and an eigenvector. So that's looking at M as a linear map on a vector space, and it's asking for invariant subspaces of this linear map. So it's saying that there's a ray. So if M acts on V, it gives you a multiple of V. Or if you look at the ray generated spanned by V, this ray in the vector space is left invariant by M. So that's a geometric interpretation of an eigenvector and an eigenvalue. But there's also another way you can describe them for Hermitian matrices, not for all matrices. For Hermitian matrices, they also arise as solutions of optimization problems, and that's what I want to talk about now. So a variational principle is variational problem is another term for an optimization problem. And the Rayleigh-Ritz theorem characterizes eigenvalues as solutions of optimization problems. Okay, so let me state the theorem. So M is a Hermitian, okay, this could be stated for complex n by n matrices, but I've stated it for real, it's the same thing. So let M be a real symmetric matrix. As we proved, its eigenvalues are real, and so we can order them from smallest to largest. We couldn't do that if they were complex because there's no order relation on the complex numbers. Okay, but as these are real, let's sort them from smallest to largest. And let V1 through Vn be the corresponding eigenvectors. And we know there are n of them because we showed that there's a complete basis of eigenvectors. Then the theorem says that lambda 1, the smallest eigenvalue, minimizes this ratio. This ratio is called the Rayleigh quotient. The smallest eigenvalue minimizes this over all non-zero real vectors, n-dimensional real vectors. Okay, 0 here is the 0 vector. I want to exclude the 0 vector because both the numerator and the denominator are 0 if x is 0, and so this ratio is not defined. So if you exclude the 0 vector and look at the minimum of this ratio over all other possible vectors, then what you get is the smallest eigenvalue. Similarly, if you take the maximum, you get the largest eigenvalue, lambda n. Okay, and in fact, it's not only the smallest and the largest that you can characterize in this way, but even the intermediate ones. So for the intermediate ones, so say lambda k plus 1, you just take the same ratio, you minimize it, but you don't minimize it over all of Rn. You minimize it over the orthogonal complement of the subspace spanned by the vectors v1 through vk, the eigenvectors of the corresponding to all the smaller eigenvalues, lambda 1 through lambda k. So let me say this again for lambda 2, let's say. So lambda 2 is the minimum of this ratio over all vectors which are orthogonal to v1. So lambda 1 is the minimum over all vectors. You solve that minimization problem, you get lambda 1 and v1. Exclude that subspace, exclude the space spanned by v1. Solve the minimization problem over the rest of the subspace of Rn. You get lambda 2 and v2. Then take v1, v2, take the subspace spanned by them, exclude that, solve the minimization problem again. You get lambda 3 and so on. So you can get lambda 1, lambda 2, all the way up to lambda n, one at a time by doing this. Or you can start at lambda n. I haven't stated it, but correspondingly you can start at find lambda n by maximizing, then exclude the subspace spanned by vn, maximize again, you get lambda n minus 1. Exclude the subspace spanned by vn and vn minus 1, you get lambda n minus 2 by maximizing, etc. So you can state it the same way. Okay, the proof is easy. I'm not going to bother with it, and I'll leave you to look at the lecture notes for that. But make sure you understand the statement of the theorem. Okay, so this was a brief lecture reviewing some linear algebra. So next time we are going to look at matrices associated with graphs. So we are going to look at the adjacency matrix of a graph and its Laplacian matrix. We'll define these and look at some properties of the Laplacian matrix. Okay, I'm going to stop this lecture here.